So we have learned about cyclic coloring and star coloring. Before moving to the next topic, let's consider one more variations of coloring. There are many variations, of proper coloring, which are, interesting in its own right, and which can be, model some other sorts of problems, depending on the context. And wait. So let's consider one more variation of the proper coloring. We say that our coloring is non-repetitive coloring, or dual coloring. Is a coloring of the vertices such that no path has a color pattern such that the first half is repeated on the second half. So meaning that if you have some path, and if this is colored by 1, 2, 3 and 1, 2, 3, then on this path the color pattern on the first half and the second half are same, so it is repeated. So we want to forbid this. Recall that the normal proper coloring forbids the case that we have two vertices with the same color and then they are adjacent. It's forbidding a path of length 2 with a repeated pattern. So this actually forbids more. This is more restrictive coloring. And we say that the dual number, and let's write it as a pi of g, is the minimum number of colors in a non-repetitive coloring of G. So where does this name duet comes from? So it's from a well-known sequence which is called duet Morse sequence. And duet and Morse and another guy, Pro, had, in the different time, they consider the following sequence. You start with, consider this binary sequence, 0, 1 sequence. You start with 1. And then you see what's written, and then you flip 0 and 1, and then write it on the right of this sequence. So you have 0, so you flip 0 to 1, then you write 1 here. And then now you have this sequence 0, 1. And then you flip all 0 to 1 and 1 to 0, then 0, 1 becomes 1, 0. So you write 1, 0. And you have 0, 1, 1, 0. So 0, 1, 1, 0 become 1, 0, 0, 1. So you write 1, 0, 0, 1 here. And then you have this. So again, you have, you flip everything. Then 1, 0, 0, 1, 0, 1, 1, 0. So this gives you this infinite sequence. Arbitrary long sequence that you want. This is one way of generating this. Another way is that every time you see 0, then you replace with 0, 1, and 1 with 1, 0. Then you start with 0, and you replace with 0, 1. And then here you have 0, 1. You replace 0 with 0, 1, and 1 with 1, 0. and 0 with 0, 1, 1 with 1, 0, 1 with 1, 0, 0 with 0, 1. You keep replacing each digit into this, according to this rule. Then you get the same sequence. So those two are two, equivalent way of producing this two-Morse sequence. And one fact we know is that there are no two overlapping identical sequence in two-Morse sequence. So why do we consider this? So here, this at the first glance, it seems that it has nothing to do with this non-repetitive coloring. In this sequence, there are many repetitions. So 0, 0 is repetition. And we have 1, 0, 0, 1 and 1, 0, 0, 1. So it has repetition. However, we can actually show that in this sequence, there are no two overlapping identical sequences in here. So these two are identical, but they are not overlapping. So it can be there, but for example, 1, 0, 0, 1, 0, 0, 1. In this case, so this and this are identical, and then they are overlapping. So this fact is claiming that this doesn't occur in this sequence. So, I will leave this as an homework, homework problem for you. So you can actually check whether this is true. But, so using that, we can actually prove that any path of any length is non-repetitive, chromatic number, the two number is 3. Let's say n is at least 4. Because if you have 3 vertices, then you can say 0, 1, 0. And 4 vertices, then you are stuck here. Okay, so at least 4 vertices pass, then you know that the dual number is 3. So it's easy to see that the two colors are not sufficient when n is at least 4. So to show this, we only have to construct one ternary sequence with 3 letters which contain no repetition. Then what you can do is you take this dual sequence, dual sequence 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 0, 0, 1. So in here, what you do is you take this 0, 0, all zeros, and you count the number of ones between two successive zeros. There are 2, there are 1, there are 0, there are 2, 0, 1, 2, 1, 0, 1, 2, 0, 2, 1, 0, and so on. We consider this sequence. This sequence has 3 letters, so this is ternary sequence. And then this is actually non-repetitive. So if you have a path, then you just color each vertex with these colors in order, 2, 1, 0, and so on. Then this is a non-repetitive coloring for the given path. Because if first, this is surely a ternary sequence, because if there is more than two, successive ones, two consecutive ones, then this part and this part, these two are the identical segments which are overlapping, so which contradicts to this claim. So there are no more than two consecutive ones. So this is indeed a ternary sequence. Every number here is between 0, 1, and 2. And also, if there is a repetition here, that means in the 2-mole sequence, we have 0 and x, say 1 many 1, and then 0, and x 2 many 0, and so on until, say, x1, xk many. And then, because this is repetition, you have again the same pattern here. So assume here we have that x1, x2 to xk, and x1, x2 to xk. So this repetition appears. That means in the original sequence we have this. So 1 to the x1 is x1 many consecutive 1. This xi could be 0, 1, 2. In that case, if we see that this part and this part, they are identical and then overlapping, so which is a contradiction to this property. So we can actually check that this actually yields a non-repetitive coloring of any length path. So from this we know that any path has the dual number 3. And also by using that, it's also not difficult to prove that for given cycle, say at least 5. So because 4 is 1, 2, 3, 2. This is okay. And then 5, 1, 2, 3. So I'm not quite sure what's the minimum length, but for long cycle, we can actually show that the cycle has a dual number, at least dual number exactly 4. And Alon, Grichuk, I don't know how to pronounce this name, and Riordan proved that any graph with maximum degree delta has a dual number almost 16 times delta square. They prove it using robust local lemma. And they prove that there is this graph G such that its dual chromatic number is almost its maximum degree square. So it's asymptotic in terms of the maximum degree is around the maximum degree square. So this is using random graph. And to know what's robust local lemma, see the chapter 0 of the lecture note. So we learned in the previous, in the previous semester, we learned it in the undergraduate graph theory. So you go there and then there is 0.6 probabilistic method. So in that chapter, you can see what this local lemma is. They use the general version of the local lemma. Let's prove some easy theorem. I mean, I shouldn't say easy. I mean, relatively simple theorem with a relatively simple proof. So if T is a tree, then we know that its dual number is most 4. So again, this can be proved with using some modification of this sequence. So let's say we have a tree T. Let's specify a root of the tree. So we arbitrarily choose one vertex, and then let's say that's a root. And then we hang in there. We just take this root, and then we just pick it up, and everything just fall down. And then we get this kind of picture. And then consider a path here. Then what does the path look like? Path may start at some vertex, and then it could go up. And it goes up, and then at some moment it could go down. But once it goes down, it cannot go up again. So all the paths are starting from somewhere, and then it goes up, and then it goes down at some point. Because this is tree. I mean, once you go down, I mean, every vertex has, in this rooted tree, every vertex has actually one parent. I mean, if you go down, that means you already exhausted the choice of parent, so there is no way of going up unless you take the vertex again. But in a path, I mean, you don't want to repeat the vertices. So for a path P, it has a vertex PP closed to the root. So because every path has this specific pattern, so it gives us some idea of maybe we can use this to color it. How? The very basic, approach is that we color every vertices here by 2 and 1, 0, 2, 0, 1, and so on. In that case, any path that, starts and go up and then never come down, in here, it has no repetition because it's a subsequence. The pattern on the path is subsequence of this, which doesn't contain any repetitive coloring. So it would be okay in that path, but for path which goes up and then go down, we have to check, whether that's also okay. So let U1, U2, and so on be the non-repetitive ternary sequence. And if we color the tree so that, let's say it starts from U0 and U1. If we color the tree so that all vertices of distance L from the root receive color UL, U sub L. Then, as I mentioned before, the path such that PP is an endpoint will be non-repetitive. However, if VP is not an endpoint, then it could contain repetition. Let's say you have this 2, 1, 0, 2, 0, 1, 2, 1, 0, 1, 2, 0, and so on. And you have this say 3. Here, let's say here. Let's say you take this path 2101 2101. Okay. In this path, what's the color pattern? It says that here this is 2, 1, 0, 1, 2, 1, 0, 1. So if BP is not an endpoint, then it does contain repetition. And why do we have repetition here? It's essentially because here we have 101. 101 is also 101 once you flip it over. So such thing is called palindrome. And we have this 101, and then this pattern here is 101. So because of this palindrome in this sequence, that's the essential reason why we have a repetition in this path. So let's actually show that this palindrome is the trouble. We have this path P, which has even length because, consider a path. If there is a path with repetition, then the first half and later half have the same color pattern, so it has, even number of vertices. So consider such a path, and we delete the central vertex, central edge. Give me a moment. Central edge of P, it gives two paths. So in here, if we delete this, then we have this path and this path. Two passes, and let P prime be the path containing BP. So this is P prime. So if both neighbors of BP in P lie in P prime, meaning that in this path P, it has two neighbors. So this and this. In the entire tree T, it has also neighbor here, but that's not in P. So it has two neighbors. If this neighbor and this neighbor are in P prime, so this is the case, then the color pattern along P prime contains a palindrome, because these two are both children of this BP. And P prime comes from below and then reach to BP and then go down. And then both of them are in P prime, meaning that in here we have this, say, alpha and this beta, then alpha, beta, alpha. So we have a palindrome in P prime. And if P is repetitively colored, meaning that this pattern in P prime also occurs later half, then this palindrome also appears in the sequence. Which used to color the tree by the levels. So that means in this U we have a palindrome, U1, U2, U3. And similarly, if BP is an endpoint of P prime, then what happened? We have BP, P prime, and then this pattern repeats from here to here. So this color and this color must be same, and this color must be same, and this must be same, and this must be same. That means in this U, say L, U L plus 1, U L plus 2, U L plus L prime, these two have the same color, these two have the same color, and so on. So then the color sequence, say leading up to BP in this P prime, so this sequence must equal the sequence leading down from PP to be a palindrome. So this shows that if we, instead of this 2, 1, 0, if we use some ternary sequence, some sequence U1, U0, U1, U2, U3, and so on. If we put these colors on this level, which is non-repetitive, and in this coloring, if this coloring of tree is not repetitive, it contains a repetitive path, that means there is a palindrome in this sequence. In other words, if we put it here, which has no repetition and no palindrome, then our coloring is non-repetitive. It's a dual coloring. So that's what we just proved. Therefore, it suffices to, say, take a new sequence which is non-repetitive, new sequence, which is non-repetitive and has no palindrome. And which contains 4 letters or 4 colors, because we want to prove this dual number of 3 is most 4. So what you do is we form u prime 0, u prime 1, this new sequence by inserting 3 after each pair of elements in this original sequence. So we get the original sequence was this 2 1 0 2 0 1 2 1 0 1 2 0 2 1 0 and so on. Now what you do is 2 1 3 0 2 3 0 1 3 2 1 3 0 1 3 2 0 3 2 1 3 and so on. Then you can easily check that this also contains no repetition and no palindrome. So by giving color u prime L to each vertex at distance L from the root, this yields non-repetitive 4 coloring of the tree. This proves the theorem. Later in 2008, Kundgen Pelsmacher generalized this argument to show that any graph with tree width T satisfy that its repetitive chromatic number is, its dual number is at most 4 to the T. Here this tree width is a parameter which measures how close G is to a tree. So for example, we know that the connected graph G has a tree width 1 if and only if it is a tree. Tree width 1 is G's tree. So yes, by generalizing this argument, we can actually bound, this dual number of a family of graphs. So we learned about this dual number, dual chromatic number. And yeah, now we move to the next topic.